All right, thanks everyone. For some reason I know why. Here, give me 1 second. Let me open this in Adobe so that it looks a little better. Okay. So, yeah, I'm glad to have the opportunity to speak. Thanks, Chris, for putting up with me delaying it. I've been one of the lucky ones who's here for the special year since September. And so finally I'm giving my seminar. So first I just wanted to tell you a little bit about what my group does at Michigan. We work in a lot of different engineering applications: environmental sensing, medical imaging, bioinformatics, power systems, and computer vision. And in all of them, the main theme that I focus on is the fact that we're collecting a lot of data in not a highly quality controlled environment. Okay, so in each one of these applications, the data collection process isn't very, very tightly tied to the engineering design of the system. It might be implemented later, and so the kind of data you get are not always extremely reliable. Okay, so in particular, the data can be very heterogeneous, like in heterogeneous type or heterogeneous quality. You might have, say, sensors that are not calibrated, and you still want to learn from those data. And then also you might have missing entries, a very popular problem of matrix completion, for example. And in the problem of matrix completion, in order to solve that problem, we assume some kind of low-dimensional structure in the high-dimensional data. Okay, we believe it's there for a variety of engineering reasons or just modeling reasons. And it's exactly that same structure that helps us when we have messy data. Okay, we can use it to do the engineering predictions we want to do, and then we can also use it to handle corruptions or missing data and things like that. So those are the kinds of questions my group focuses on, looking at a wide variety of models, usually unsupervised learning, and trying to answer whether we can still estimate those models in the presence of these data quality issues. Okay, and I wanted to mention that you guys all know there's an IS workshop on missing data challenges. We're really excited about the speakers and the keynote speakers too, who we have coming. So if you haven't registered yet, then you should. Okay, the work I'm going to talk about today is work by my student Amanda Bauer. She's here. She's visiting for a few weeks. So if you want to talk to her, you should. And what I'm first going to do is just introduce the problem at a high level and give you the motivation for our approach. So the problem of preference learning is one where we have some number of items that we would like a ranking of. Okay, we want to know what's the best item under some criteria all the way to the worst item under that criteria. So say we have n pairs of shoes, and Zappos wants to know, do we think, what's the ranking of these items in terms of how comfortable they would be? What do people think? And so that if I search the website for some comfortable shoes, they can, give me a good recommendation. The problem is it's impossible really to ask any humans to rank these items when n is very large. Okay. And so what people do is collect k-wise comparisons, meaning they ask for some small k, somebody to take those and rank that set. Okay, and commonly k is 2, so there's a lot of literature on learning rankings from pairwise comparisons. Okay. The motivation for this general problem of preference learning is extremely broad, so you can imagine certainly the people who are reviewing for ICML right now, they would like a ranking of all the papers with the worst ones, the ones that are admitted, the ones that get a poster, or, well, I guess ICML is all orals, but maybe spotlights or whatever. Or like anomalies in some kind of engineering system. So for example, when I was at Wisconsin, I worked a lot in network data at that time and talked with some of the guys who managed the network. And every day they had hundreds of potential attacks on the network. And the network was really secure, so nothing had ever happened, but it was part of their job just to go and investigate the logs and like see which ones of these could potentially become a problem and try to make the network secure, okay? But there were so many, and it really wasn't their first job, so what they would have loved to have would be a ranking of those potential attacks in order of basically priority of danger or how bad it could have become in some setting, okay? So there are just many, many applications of this kind of ranking and learning those from data. And there are a lot of really big challenges in this problem too. The problem of rank aggregation is one where different people will provide different preferences, and you want to find one ranking that matches all of them in some sense. Usually the comparisons are noisy, or maybe you get limited feedback. And like, for example, in the case of pairwise comparisons. And the challenge that we're going to focus on today is that often these comparisons reflect some kind of intransitivity, okay? Even from one person who's giving pairwise comparison results, when you look at them together, you'll see intransitivity. So intransitivity, just to be clear, is a situation where you have a preference cycle in the data. Okay, so here we have a triangle where loafer is preferred to flip-flop, boot to loafer, and flip-flop to boot. Okay, and this is a problem that's in many, many data sets. Okay, so this is just a listing of several different pairwise comparison pairwise comparison data sets. This is the number of valid triplets, so we only look at these triangles in the data, okay? This number of valid triplets in the data set. And then we have different kinds of what's called stochastic transitivity violations, okay? So as an example, a triplet would violate moderate stochastic transitivity if I is better than J, and J is better than K, but then I only beats K by some probability, or meaning frequency in the data, that's less than those other two, okay?
I have a question.
Yes, please.
So generally, different people have different preferences, so I guess what you have is a mixture of consistent transitive policies of different populations, and when you mix them together, you get this intransitivity.
Yeah, that's an excellent question. So the question is like, these numbers here, they could simply reflect exactly the first bullet on the previous one, that you have lots of different people with different preferences, and they're giving some kind of inconsistent with each other results. And that's certainly possible. What was I going to say? In a lot of these data sets, there really are sort of preference focused. But in others, you kind of believe, like in, let's say, NBA, we're just looking at, matchups, that there should be like a best team to a worst team. And what we're going to do is ignore the problem that you just said, look at a different problem, which I hope I'll motivate to you before I show you the theory. And then, future work is certainly interesting to think about both of those things simultaneously. And maybe I can, actually I have one example here. So I'd have to think about it. I haven't thought about this to be completely sure, but a weak violation is one where actually this probability that even though I beats J and J beats K, I doesn't beat K in frequency. K beats I. So I don't think you could get that by aggregating individually consistent. But I'd have to think if that's a precise statement. Yeah?
Just to sort of support your point in Go, whether one player beats another is not necessarily a transitive relationship. At least historically over here.
And actually, that's interesting, and I hadn't thought about this in the game playing context yet, but I think that our motivation is actually extremely relevant for that. So let me get there. Okay, so here's an example of data from this last New Yorker caption contest. Is everything okay? Okay, thanks. So in the New Yorker caption contest, they in the back page of the New Yorker, they show like a cartoon without a caption. They've been doing this for as many years as I've been reading, which is a really long time, and I'm sure longer than that. And more recently, they started crowdsourcing the winner, okay? Because they basically got thousands of submitted captions, and the editorial team had to decide which ones were the best. And so now they show them online and ask people to decide if it's funny or not, and then the people with the most votes, the captions with the most votes win. So here are 3 captions, and in this data set, they actually did a pairwise comparison where they asked you, which one of these 2 captions is funnier, okay? So I think all of them are pretty good. But what's interesting, each pair first was compared at least 89 times, so we have a pretty good averaging here. A was better than B 60% of the time. B was better than C 62% of the time, but C was better than A 66% of the time. Okay, so we have a weak transitive relationship here. Okay, so now I've been saying I want to motivate our particular approach, and I'm going to start out by doing that by talking about an application that we will look at later, which is in congressional districting. So I don't know, is there anyone in this room who can vote in New Jersey? Nobody. So it's not as good of an example, I guess. I gave this talk on Monday at Princeton too, and lots of people could respond. But these are the federal congressional districts in New Jersey, and we know, nationwide there's been recently an effort to reduce gerrymandering, or at least talk about it, and talk about the way these districts are drawn, right? The process and the choices that people make to draw these districts. And in New Jersey, it's politician commissions that draw the districts, and it's just a committee. And actually, for both state and federal congressional districts, these politicians who are chosen by their political party have never been able to come to an agreement. Okay, so in this case, I found online that for the state districts, state-level congressional districts, for the last 40 years, they've not come to an agreement. And then there's some, caveat in the Constitution that says, okay, if you can't decide, then you have to give 2 maps to the Supreme Court, and the Supreme Court decides. Okay, so it's difficult to draw these maps in a way that people think is fair and sensible. And the only criteria in the Constitution for state districts in New Jersey is that the districts must be contiguous and keep cities intact. And then I want to focus on this one. They must be, quote, nearly as compact as possible. Okay? So this word is not defined, compact. It means something different to all of us, but that's the only law that guides these congressional district boundaries. Okay? So this is a really interesting set of maps from 538. You could do this for any state if you're from a different one and interested. These are the current federal districts that I showed you, and this is just an algorithm that tries to find districts that will favor Republicans or Democrats using voting data from only the past 12 years. So, there's so much publicly available data, and it's so easy to analyze these days that you could really change the makeup of the House representatives from New Jersey with a change in one of these maps. And this map, they tried to use some kind of algorithm for compactness that still follows boundaries of counties in the state. So I just show this to say that there are many, many different ways to draw them, and they have like a very big impact, okay? So the data that we looked at is from a group at Harvard who wanted to take this word compact and ask people whether they thought that some existing federal districts were compact, okay? So they had images like this of districts from throughout the United States, and they asked people to answer whether one of the two was compact, okay? More compact, right? So I want to go through 5 pairs. If you want, at the end I'm going to show you like what the percentages were in the data set, so if you want to write down what your preferences are. But I do want someone to tell me, of these two, which one do you think is more compact and why do you choose it? Yeah. Why do you say it? B is more compact. It doesn't have like this non-convex hole right in the middle. Okay? All right, how about A and B on this slide?
Well, I didn't hear your definition of compact, but
Yeah, no, you know, he said...
Covering by spheres, that's classical definition of compact, A is compact.
Then A is more compact, yeah.
Your
So I like that. So first, I appreciate that you said I didn't hear the definition of compact. So that's absolutely correct. None of the constitutions give a definition of compact, and in the Harvard study, they also didn't give one. Okay, but I appreciate your definition. So fewest number of spheres to cover it. So we'll say A is more compact. All right. Anyone have a preference here? Yes, Emery. Any reason?
I don't know.
Most people, yeah, most people don't like this. Most people don't like that. Okay, number 4. 2 people who haven't answered has to, no, 2 other people have to participate. Yeah. Why? Okay, ratio of perimeter area. Good. No, that's good. Okay, last one. No one else wants to give me their opinion? This one is really hard, I think, because this thing is weird. I think A is more compact. And, basically this, like, trying to stretch itself out, that's what, yeah, Bianca.
Who lives in that stretch?
Yeah, who lives right here, yeah. Okay, so.
But then again, politically, you cannot, I guess the reason why it's hard to define compact is because those could just be due to natural boundaries.
Yeah, no, that's true, yeah. Yeah, if someone was going to bring up that question, like, is there like a lake on either side of this, for example? Is it an isthmus? I was going to say, let's assume for the time being it's not a natural boundary. But, natural boundaries and also like town boundaries can look weird, right? So it's part of the issue. Anyway, the reason why I'm doing this, this exercise and specifically asking you for the reasons is to then talk about what were some of their conclusions after they took these pairwise data, okay? So you'll notice here, if you did keep track of what you thought, there are 3 pairs that have a valid triplet, 2, 3, and 5, okay? So you may or may not have been transitive on those. And in fact, in the data, it is not moderate. It doesn't satisfy moderate stochastic transitivity on this triple. Okay, so 70% of people say A is more than B, 90% say B is more than C, but then A is more than C, more compact than C is only true 60% of the time. Okay. And the conclusion that the authors in this study had was that basically this pairwise approach allows people to focus only on very specific features like ratio of area to perimeter or degree of non-convexity. Okay? And when you only have a pair, you focus on some features that distinguish just those 2 items. instead of like all of the possible features of compactness. Okay? And in their paper, they therefore said these data are not very useful, so instead we're going to collect rankings. And they collect rankings of like many districts. In fact, they even asked some people to rank up to 100 of the districts, and they found there was a much more consistent output from those data. Okay, but our goal is not to abandon pairwise comparisons altogether, but just model exactly this behavior and see if we can still learn the ranking from these intransitive pairwise comparisons. Yeah?
People try to correct this, like they found this in their data set that these three have this triplet has this problem, just tag these three and try to fix that error.
So tag them and fix the error in what way? Do you mean only provide them together? Sorry.
Three triplets together or something.
Like, so always show those three together, or if you're going to.
It's more like you start off with two, then you identify the triplets of each one.
Yeah.
And present those back again, and you keep doing that, rather than just asking for a whole bunch.
Yeah, no, I mean, that's a great idea, right? Kind of an adaptive sampling or presentation technique. I mean, and there's actually a lot of work in adaptive comparison making. So that's a really a good idea. So yeah, our approach will just be to try to model the behavior instead of requiring these groups to get bigger. Okay, so the idea, hopefully, is that you saw these pairs and you use specific features, but then when you see, let's say, even all of them at once, then you're forced to consider more, if not all, of the features of these different districts to make your decisions. Okay, so another high-level picture of then exactly how we do this. We base our model off of the Bradley-Terry-Luce model that uses features. Okay, and so first I'll show you that model. Every data point here represents one of the items, one of the districts, for example, and it has an embedding in some feature space, in this case illustrated with 2 dimensions. And then there's some unknown vector we're going to call W, and that's a judgment vector that the inner product of that vector with the individual items will decide its utility. Okay? So the utility of these items, 2's utility is higher than 1, higher than 5, higher than 4, and 3. Okay? And then for a particular pairwise comparison, we get, with Bradley-Terry-Luce, we get a probabilistic result. So the further away these items are on this projection, meaning the farther away their utilities are, the more likely, with a Bernoulli probability, it is to beat that item in a comparison with random data. Okay, so like 2 is much more likely to beat 3 than it is likely to beat 1. Okay. So we just changed this model to introduce coordinate projections. Okay, so if I were to instead project onto the x-axis or the y-axis and still assume alignment with W, okay, so meaning that feature x is better over here and feature y is better at the top, then I get a new set of orderings on these, okay, and basically new probabilities of different items beating each other. And so when a particular feature is salient and important for that comparison, when you see just those 2 items and you use a single feature, then you can have intransitive comparisons, okay? So if 4 and 2 only use feature x, only use feature y, then 4 is better than 2. 2 and 5 use x, then 2 is better than 5. But when 4 or 5 use either x or both of the features, then we would see that 5 is better than 4, okay, with some probability.
Sorry,
Yeah.
I have a fundamental question. Multidimensional data is not naturally ordered. I mean, there's no ranking which is really correct in more than one dimension.
Mm-hmm.
So you have this case it's two-dimensional. Generally, there are many more. So I'm not sure. I mean, you're going to draw a line somehow through points which are multi-dimensional. That's why it's so hard to line people, because we are not one-dimensional.
Absolutely. So the question is, multi-dimensional data are not naturally ordered. So the Bradley-Terry-Luce model has an extremely strong assumption that there is a d-dimensional vector embedded in the same d-dimensional space that dictates the utility, the how good or how important each coordinate is. So basically, now I can say my inner product of the items embedding with this single vector.
So essentially, you just choose a projection of the data.
Or you try to learn a projection.
Eventually, one-dimensional projection.
Exactly.
And there you rank.
Exactly.
So the whole point is learning the weights of the different features.
Exactly.
Right.
Okay, good. So now we're almost at the part where I show you what theoretical results we can have on this model. But I just want to mention that there's a lot of work out there on modeling violations of rational choice. In fact, there's a lot of social science papers that have commented exactly on this phenomenon and sort of tried to give econometric type of models for it, but not actually trying to overcome it in a data set. And then more recently, lots of different groups have worked on learning features, for example, for pairs that are context dependent, or learning utilities that are context dependent, meaning dependent on the comparison that's being made. But some of them, they all differ from the work that I'm going to present in some way. And if you're interested in the relationship, I'm happy to explain it more. So our work will give a convex model that still allows intransitivity. It has this salient feature characteristic, which is inspired from social choice literature. It allows us to generalize to items we haven't seen and pairs we haven't seen, because we rely on the fact that we have features. Okay, so you have a new item and you have its features. Once you've learned the W in BTL, then you can still find its ranking. And it makes a direct connection between these intransitive preferences and one universal ranking. Okay. And I will show you our sample complexity guarantees. Okay, so let's start by just defining the mathematics of the model. We have n items, and each one has a feature vector. I'm going to call it U sub j, which is in a d-dimensional space. Okay, so the matrix of all feature vectors is d by n. And we're going to assume this Bradley-Terry-Luce model. So there's a single W star whose coordinates dictate the utility of each coordinate, each feature for each item. Okay, and that's what we want to learn. We want to learn this vector. I'm going to let P denote the set of all pairs. Okay, so a set of size n choose 2. And then S sub m is the set of independent pairwise comparison samples that we make. Okay, so ij is some element in P, and then y is some outcome, either 0 or 1, or some binary variable that says whether I is better than P or whether I is better than J or J is better than I. Okay, and in all of our theory, we draw our comparisons from this set. From the set of all possible pairs independently with replacement. Okay. So how is the probability of that? How is y in the previous slide, that outcome variable, related to I and j? This is where our model differs. We introduce a selection function tau that is basically going to do a coordinate projection that depends on any specific pair. Okay? So that's tau. It takes 2 of the items and outputs some subset of the D features. And then the outcome variable is Bernoulli with some probability. That's dictated by this utility that's constrained only to the set decided by tau. Okay? So this utility of the item, the inner product of U with W star, is now dependent on the context of I and J, the particular pair that you're considering.
So Laura,
Mm-hmm.
so this is sparse logistic regression. I mean, that's the signal.
Yeah. No, it's extremely related to sparse logistic regression. But what we're seeing is like pairwise, pairwise, I don't know, ranking arguments, or do you know what I mean? So yeah, the only difference here, let me say it this way: the only difference is like the what I would call X is a pair, and so it's not independent of other values.
Sure.
Like I1 and J and I1 and K are related to each other. Okay, and so if if the tau function selects all of the coordinates, then we get a full feature utility, and that's the special case of feature BTL that I mentioned earlier. Okay.
So non-linear ranking is not out of the game. I mean,
You mean?
so I want to rank the complex numbers, so I'm usually doing it by magnitude. This is a non-linear projection. Oh, I don't know.
So you're saying, so tau here is a linear projection. This is how I've defined it because it's a coordinate selection. But are you asking, like, could I generalize that? Or
Could I work with some non-linear function of the coordinates?
it's an interesting question. Right here we're only using a linear function that we output a linear projection.
What we could do is, of course, use kernels or something like this to map it.
Yeah, no,
And then
certainly.
use the linear function, but you're not doing it.
And another generalization that we thought about is like just an arbitrary projection here. It doesn't have to be a coordinate projection. Maybe we can talk about those possibilities at the end. Okay, so we estimate this model with maximum likelihood estimation. This is the objective function you would see in also logistic regression. And we're trying to estimate these utilities. Okay. And the results that I'm going to show will be sample complexity results for the maximum likelihood estimator on our model. Okay. Okay, so the first result that we have is an identifiability result. So if we had infinite data, would we be able to recover W star? Is it possible? Okay. And we have a necessary and sufficient condition. So it's that the span of the differences of these feature vectors in context should be the whole space. Okay. And there's one sort of obvious example why this should be true, that, for example, if none of them select the last coordinate, then we can never know if W star finds that coordinate, that feature, to be important or not. So now I need to define three quantities before I can give you the sample complexity theorem. So B star is the maximum absolute difference between the pair's utilities in context. Lambda is the minimum eigenvalue of this expected matrix. Okay, expectation is taken with respect to a random pair chosen from P. And that matrix is the outer product of the two, or of the difference vector in context. Okay? And then beta is just the maximum difference between two feature vectors in context, in the context that is considered for each vector, pair of vectors. Okay, so B star, lambda, and beta are here on this slide. And this gives the sample complexity result. So we let W hat be the maximum likelihood estimator. And we have two conditions. First, lambda, that minimum eigenvalue, must be strictly positive. Second, we need some number of measurements, meaning draws from the set of pairwise comparisons. That's roughly like d log d or log d over lambda, whichever one is bigger. Okay? And then with high probability, we can control the error between the true generative W star and W hat, which is the MLE. And that error it has like this lambda again in the denominator, and depends exponentially on that maximum absolute difference of the utilities in context. But the good thing is this number of samples is in the denominator, so we can take it to be large enough to control the error to what we need it to be. Okay. This is the same thing, just compressed, and I just wanted to comment on a few things. So first, this lambda here actually is positive if and only if the model is identifiable. So it's another equivalent identifiability condition. So it's very natural that it should be in the theorem. Okay. This exponential dependence on B star is in the other results answering these questions. They have claimed that they think they see in simulations that it's not necessary, but we also couldn't get rid of it from our analysis. And then if we let these three quantities that I mentioned on the earlier slide be roughly constant, it says we need d log d measurements to control our error. Okay, and that's a nice number because the BTL requirement without features, so just general utilities, is roughly d squared log d. Yeah. The goal is to recover W. And do you want me to show the MLE or?
Well, I guess the question we were discussing is why do you want to get parameter recovery for W star? I thought the goal was to just minimize the feature loss on probability comparison.
That's a good question. So our goal is to give you a full ranking. So I suppose you can probably go back and forth between these things, but we want W star because it tells us the utility of every item, the full feature utility of every item.
I see. Presumably you could have some other function, give two items and it'll just tell you the ranking, making some more complicated thing.
Yeah.
I mean, you're paying a lot there in sample complexity to actually recover the W star.
Oh, I see. You think that there's a significant difference? What would it look like?
Well, I don't see why you have to pay lambda at all if you just want to minimize the feature loss.
And even the exponent only shows up because you're using a sigmoid, so that sigmoid has this lower Lipschitz, which is this.
Right.
Yeah.
So you can avoid that if you just get it right.
I see. Okay, I'll have to think about that. Do you have any thoughts on that, or not right now? Okay. Yeah, so I certainly don't think this is optimal, that this is, necessarily the best possible rate, but it might be surprising if you could go from probabilities to rankings without paying anything, but we'd have to think about it. Any other questions? Okay, so we have a few corollaries as well, and this one I just wanted to show is for sample complexity of full feature BTL, which we looked through. We couldn't find. If anyone knows of a place where someone else has proved something, to let us know. So in this case, we can tell you what lambda is. Okay, so lambda is roughly the minimum eigenvalue of this outer product of the feature matrix divided by n. Okay, and then we just plug that in, of course, to our result, and we have a better grasp on what m has to be to make this small. Okay. And comparing this one to BTL without features, the result for that, like I said, is d squared log d. It's interesting to see that, again, we require only d log d samples to control the error, and so maybe it's sort of showing that when you have features, when you make this sort of strong assumption that the features are defining your, your preferences, then you can actually gain something in sample complexity. Okay, we have two more corollaries that I'll just tell you about. One of them looks at a selection function that selects just one coordinate in every pair. And this one basically shows that it depends on how many times the selection function, or what fraction of time the selection function observes particular coordinates. Okay, and if everything is used sort of equal number of times, then we have d squared log d sample complexity. And finally, we tie this learning of W star to learning the ranking. So we have a corollary that shows you the error in the full ranking, which basically shows that this is the difficult situation, which is very natural. If two utilities are very close, then it's difficult to identify the full ranking. And the corollary gives you what the Kendall-Tau correlation will be for the ranking by W hat versus W star. Okay, are there any more questions on the theoretical results? All right, so let me show you a little bit of data. Did you have a question?
I don't even know if it's a well-thought-through question, but so you have an error in W star to W, and I imagine so that from that error you can enter some error on the ranking. But it feels to me that there should also be a threshold at which if you are within, if you are that close to W star, your ranking should be right. And I'm just wondering whether, it depends on how spread out the errors are, of course, and how much room you have.
I'd have to look again, but my memory of this theorem, it's like the bound depends in such a way that I think you would get that, like below some epsilon between W star and W hat, the Kendall-Tau correlation will be 1. Does that sound right to you, Amanda? Yeah. So we can look at it together to make sure, but that's a good point. All right, so empirically we did first some synthetic data just to do the following two things: show that this model does generate intransitive pairwise preferences, and then to illustrate the sample complexity rate that we talked about and investigate model misspecification. So we have 10 features, 100 items, and we draw the coordinates of the features in W star with Gaussian random variables. And then the selection function we use, so all the work that I've done so far is assuming a given tau, okay? So we're assuming that you know the behavior of tau. And in this case, what tau we're going to use is to say, take the distance between the feature value in U1 and U2, and the largest t distances we're going to keep and consider, okay? So, you can imagine that the features that seem very different between the two items are the ones that you use to make your comparison. Okay, and t then is a parameter here, so we have to talk about how many coordinates per pair of vectors that we're choosing. So in this figure, we just demonstrate how the model has violation of rational choice. So orange, blue, and green lines are these stochastic transitivity violations that I've defined before: weak, moderate, and strong. And then this red line also shows what we call a pairwise inconsistency rate, which just means that the pair comparison is not consistent with the overall ranking. And this plot uses t equals 3. Oh, sorry. The last comment I wanted to make here was as t increases, so this is that number of features that you select per pair, then you get fewer intransitivities. And of course, with full feature BTL, then you'll have no intransitivity in your data. Okay. This plot looks at the estimation error in W, and we use the top 3 selection function. Okay. And first of all, so this green line is for, so the data are generated with t equals 3, and then the green line is we learn MLE with t equals 3. Okay, so we know exactly the model specification. And this rate is the rate given by our theorem earlier. The bound is not on this plot, but the rates are exactly the same. And if we change t in the MLE, we don't get the same rate. Okay, so it seems very sensitive to model specification. This is just the same thing, but with Kendall-Tau correlation, which maybe isn't quite as sensitive, but still is sensitive to model specification. Okay, so then on the real data, in the district data that I talked about earlier, after collecting these pairwise comparisons, they kind of gave up on those and collected the full ranking. So we have both of those data sets, which is really great. And here are the results from our method and then 3 other methods in this area and trying to learn these rankings. Okay, so the way that what these numbers are is the Kendall-Tau correlation of our output ranking with each of the individual rankings that are available on each of these 7 data sets. Okay, so there's like 7 different collections of rankings. And yeah, I guess that's all I was going to say. So the numbers are not very high, and we know what the inter-user Kendall-Tau correlation is as well, and they're also somewhat variable. But it's still a lot less variable than the pairwise comparison data initially. So you can see like the best one is this data set, and it gets a 60 or a 0.6 correlation. Okay. And here RankNet is a deep net that tries to learn these utilities using a deep net, okay, to do the ranking, and they do well on one of these data sets and pretty well on others, but still not as well as when we consider this idea that there are certain features being used. We also looked at the Zappos data set, which has only pairwise comparisons of shoes. And in this case, these are what are called fine-grain comparisons, where they gave you like 2 tennis shoes and asked which is more of some characteristic, and those characteristics were open, pointy, sporty, and comfortable. And basically, we see that we're doing as well as all of these other techniques. Unfortunately, we can't check the transitivity in the data because there are no valid triplets in the Zappos data set. I guess we could try for other cycles. But one thing that we did think was interesting was that when we did, cross-validation for our t parameter, it never used all the features, like between half and, well, the smallest was like maybe it used 40% of the features, and then it would use maybe 2/3 at the most. So not all of the features in the data are really necessary for getting these rankings. Okay, so the things that we're really interested in relate to ideas that were already mentioned. So like I said, we need to know what the tau function is. And we, tried something like this top T because it was sort of posited in some of the social choice theory. But what we would very much like to do is learn it from the data. And in fact, the features that we can define, so like for the district data, for example, they have several features like ratio of perimeter to area and things like that. We could come up with those features, but those aren't necessarily the features that individual people are using when they're making their decision. And so you can imagine if we have to learn the selection function, in some sense, we could also say we're simultaneously learning the features. Okay? Yeah? So the question is, are there techniques that basically use the data that's available and try to do something nice with drawing the districts, like some metrics for what would make a good district, and then actually trying to use that? So they actually do, but not people who are actually drawing them. But like that 538 website has algorithms for drawing compact boundaries that still follow the counties. And a lot of people in making these legal arguments have been trying to come up with, rules, let's say, for example, that the way it's drawn should not like disallow a competitor an opportunity with some what's the word I'm looking for? It shouldn't be outside of 10%. If the population is a certain makeup, then they should have that same chance of winning, type of thing. So, none of them have been adopted, not by the Supreme Court, and that's what that case that was there. They considered trying to make those kind of arguments, but none of them are very clear that it's the right way to go either. So, yeah. Uh-huh. Give a ranking of the candidate districts?
No. So let's say you have candidates that are running for the
Okay.
or something like that.
Yeah.
You have 6 candidates, and you know how in a particular region people will vote based on who's registered and who's not.
Uh-huh.
If I give you a desired ranking, can you find the closest drawing that of districts that would give them?
Yeah, absolutely. That's what I was trying to show with those 538 slides earlier. So basically they can choose a way to make it be like 60% Republican or 75% Republican congressman or 75% Democrat congressman. So basically, if you tell me I want these people to be higher and I want these people to be lower, I could draw the map to make that happen, no matter what it is that you want. Yeah, that's a good question, but I'm confident that the answer is yes. Yeah. Any other questions?
The main issue here is to model human behavior or to model an algorithm for finding consistencies in ranking in general.
So are we trying to model human behavior or trying to deal with consistencies in ranking in general? So I guess originally when we did it, it was human behavior that motivated us. But like actually the sports example that you gave, I sort of realized often the reason why A beats B, B beats C, and C beats A is because of features, right? Like their defense is better and their offense is poor. Or, it matters on not just that this team is better, but their particular features of those teams makes them able to beat this other team. So, I'd have to think about if there are other examples, and if I can try to make the argument that we've identified something, that actually feature projections are going to be the way that intransitive pairwise comparisons occur. But I wouldn't say that yet because I've only looked at a little bit of data. Okay. Thanks.